We'll now talk about one of the most important results in all of statistics, the central limit theorem, which we started to look at last time. And it says this: for all samples of the same size n, if n is bigger than 30, the sampling distribution of the sample means can be approximated by a normal distribution. And it's notable that we have the same mean, so the sample distribution of the sample means has the same mean as the population mean, but now the standard deviation is the old standard deviation, population standard deviation, but divided by radical n. And we know that if the original population is normally distributed, then we don't need n to be bigger than 30. Okay, so kind of the setup is that your original population has some mean and standard deviation, and it could be any distribution, not normal. Could be anything. And then we're imagining taking random samples of size n. So the two things you need to check are whether your population has a normal distribution, or if not, then you'd like the sample size to be bigger than 30. If either of those hold, then the mean of your sample means, which we denote mu sub x bar to indicate that it's the mean of the sample means. So the mean of the sample means equals the mean, population mean. Now the standard deviation of the sample means is going to be sigma divided by radical n. Alright, so once we know that, we can use all our results about normal distributions, z-scores and all that, to find probabilities. So when we're doing that, notice that for our z-score here, for our z-score, we're going to need to use, instead of sigma in the denominator, we're going to use sigma over radical n. So if neither of those two requirements hold, then we're out of luck. We won't be able to use our previous results. So when solving problems, we need to be aware of two things. One is that we have to check the requirements. So either the original population is normally distributed or the sample size is bigger than 30. And then we have to be aware of whether we're calculating probabilities for an individual value or the mean of a sample. Okay, so if you're just for an individual value, here's your z-score. But for when dealing with sample means, we know sigma is replaced with sigma over radical n. Okay. Some notation, we'll use the subscript x bar to indicate when we're talking about the sample means. It's not important when we're talking about mu because they're the same, but when we're talking about the standard deviation, it is important. So sigma sub x bar is different than sigma, right? We also call sigma sub x bar the standard deviation of the sample means. We call that the standard error of the mean. Here's an example. You can pause the video if you want to read it through. Part A is the same type of problem we've done a bunch of times. But now look, Part B has us doing the same type of problem, but now with a sample of size 27. The first problem is just like the problems we've done before. We sketch a diagram, shade in the appropriate area, find the z-score for our value, look up the probability in the table, and then we have to subtract that probability from 1 because it's a right-hand probability. So 85% probability that the weight of an individual is bigger than 148 pounds. Now if we look at the second problem, part B, probability that a sample of 27 randomly selected adult males has a mean greater than 148. Well, we have to check whether one or two conditions hold. If the original population is normally distributed or n bigger than 30. Well, the sample size is not bigger than 30, but the original population is normally distributed, so we can use a normal distribution and use the central limit theorem. So central limit theorem says that our mean for the sample means is going to be 189, the same as the population mean, But our standard deviation of the sample means is going to be this new sigma divided by radical 27, which is this. Notice it's smaller. So a lot smaller standard deviation. So the distribution of our sample means will look something like this. If you compare to the original population, which is more spread out because larger standard deviation. So now when we find the z-score, we find that it's minus 5.46. Remember, within 3 standard deviations is 99.5% of the population, and this is more than 5 standard deviations away. So you look up that number in the table and you're going to get this as a probability. So subtracting from 1 you get 0.999. So almost 100% probability that the sample mean is going to be bigger than 148. So if you compare that with, it was 85% for an individual. So the probability was 85% for an individual, and it's about 100% for a sample of size 27. Some takeaway remarks. So the standard deviation of the sample means is going to decrease with the sample size because we divide by radical n to get the new standard deviation. And it's going to follow that when you have a large sample size, the sample mean is going to tend to be closer to the population mean. That will be important when we look at confidence intervals coming up.